Well, good evening and welcome. I'm so happy to see all of you here this evening. As I was just mentioned, I am Frances Hellman. I am the Dean of Mathematical and Physical Sciences in the College of Letters and Science at UC Berkeley. I'm also a professor of physics. And, some of the things people are talking about tonight are things I am deeply interested in personally from some of my research. I'm so glad to see so many of you here this evening. Dean Mike Bochen and I are very gratified by the interest that this series, Basic Science Lights the Way, has generated amongst alumni and friends. So much so that we're actually planning to continue it, even when we're able to gather in person. And this has been such a great way to get people together and to have presentations and things. Seeing so many of your names and faces from outside the Bay Area is truly the silver lining in this pandemic. So tonight, our subject is innovations and adaptations for sustainability. Needless to say, a huge topic whose surface we will merely scratch tonight. As you can imagine, Berkeley is a leader in addressing things like climate change, innovations in energy, and the environment writ large. And tonight we're going to show you how basic science research provides the engine behind the advances that will lead to adaptation and mitigation. We toss around the term sustainability a lot, but I think it's worth defining it here and allowing it to provide a theme for this evening's presentations. The UN World Commission on Environment and Development defined sustainable development as development that meets the needs of the present without compromising the ability of future generations to meet their own needs. In other words, what kind of world do we want to leave for future generations? That's the question that inspires our speakers this evening, as well as our moderator, Charles Marshall. Charles is the Philip Sandford Boone Chair in Integrative Biology and Paleontology with a joint appointment in Earth and Planetary Sciences. He's also the director of the University of California's Museum of Paleontology and chair of the Berkeley Natural History Museums. Charles's research centers on unraveling the history and evolutionary dynamics responsible for life on Earth. And I've heard him give talks on this topic himself, and they're fantastic. So I recommend some future thing where he gets to really feature his own work. He typically develops new quantitative approaches to integrate relevant fossil, geologic, biologic, and genomic data. His current research interests focus on the origin of life, to the synergy of tectonic processes and climate change on changes in diversity on geologic timescales, all the way to estimating the total number of T-Rex that ever lived, a number that I'm curious about. So with that, I'm going to turn the stage over to Charles. Take it away, Charles.
Thank you, Frances. A pleasure to be here and a great pleasure to moderate today's event. We live at a time of decelerating, but still growing population and ever-increasing resource extraction. The burden is immense, far heavier than any one of us can bear. Yet at Berkeley, I've been astonished at the depth of commitment to make a difference, at the breadth of research being undertaken that will impact our long-term quality of life. As a paleontologist, I've always been struck by the indirectness of the path to major evolutionary innovations, such as multicellularity or flight. Incidental changes become crucial and thus are often termed pre-adaptations. Similarly, pre-adaptation is key to developing a generative future for us all. What do I mean by that? Today, we'll hear from just 3 of the many world-class innovators at Berkeley who exemplify how blue sky thinking, scientific curiosity, and prowess becomes a pre-adaptation for environmentally and societally relevant innovation. And so it's with great pleasure that I now introduce or ask our 3 speakers to tell us a little bit about what they're doing in the context of developing a sustainable generative future. As already said, we encourage questions. Please type them in the chat and we hope we can get to them all. And so we begin with nature on a grand scale, the Amazonian rainforest. Please welcome Paul Fine, Professor of Integrative Biology. He investigates Amazonian rainforest tree diversity and works to understand the factors that influence how new species are formed and how species coexist. He's an ecologist and an evolutionary biologist who's been studying the Amazon forests for over 20 years, mostly in Peru, Brazil, and Colombia. Paul, the screen is yours.
Thanks, Charles. It's really great to be here and to have a few minutes to tell you a little bit about some of the things I'm really excited about. And even though I do Zoom as it's my main occupation these days, it still takes me a second. All right. And there we go. So I'm going to talk today about sustainability in Amazonia, Amazonian forests. And there we go. The Amazon has this gigantic rainforest. It's the largest contiguous rainforest on Earth, and people refer to it as the lungs of the world because it produces an astonishing amount of oxygen. And it's also important kind of globally and climatically because it's such a storehouse for carbon. It's a sink for carbon because of these gigantic forests that cover almost the entire northern half of South America. And it also is super important because it's got the highest concentration of species in the world. Almost every group you think of, insects, I study plants, I'll tell you a little about trees in a bit, birds, reptiles and amphibians. I mean, not penguins, of course, but definitely almost any large group of organisms, the highest concentration is in the Amazon basin of species. And there's also just an amazing variety of indigenous languages and cultures in the Amazon, including over 50 that are rejecting contact from outsiders or have never been contacted. And here's a picture of one such tribe in Brazil. And I'm going to tell you about tree diversity, and that's what I study. That's my focus. And this is a typical shot when you're flying in a small airplane over the western Amazon. This is in Peru. And you can see here, there's just, it's so gratifying when you're flying. You see just endless sea of green as far as you can see, intact forest in many places of the Amazon. And some work I've been a part of estimating exactly how many trees there are in the Amazon basin and how many species. And the current estimate now is 390 billion trees across the Amazon basin, and they represent at least 16,000 species. And just to give you a little bit of context, in the US and Canada, which is a much larger land area than the Amazon basin, there are about 600 species of trees. So it's quite different, the difference in diversity. And this part of this work to estimate tree diversity, we were interested in what was the relative commonness and rarity of these trees. And we were astonished to find out that half of all individual trees is made up by only 237 species of those 16,000. So some species are really, really common, and other species are really, really rare. And to really understand diversity, it's really important to understand what factors are influencing commonness and rarity through space and time. One of the hypotheses to understand commonness and rarity of Amazonian trees is that humans have been managing forests for millennia. And by selecting various species that are useful and promoting the success of those species and using fire and dispersing seeds and changing the soils is one way that humans have been managing forests for thousands of years. So the questions that we have is, what is making these trees so common and others so rare? And to what extent are humans playing a big role in this? And so what we've been doing is focusing on one group of trees that are really important to humans, and those are palms. Palms provide material for housing. They provide a lot of nutritious fruits, and there's dozens of different species of palms across the Amazon. Some of them extremely common, and some of them very rare. So in this grant that I just got over the last year, that we're going to set up actually just in a few months, we are looking at a couple really large areas, one in Ecuador and one in Peru. And we are going to be counting canopy palms of many select species, some of them very common, some of them very rare, and looking and measuring a bunch of environmental variables, but also studying their history through time and the role of humans. And I'll tell you just a little bit about how we're going to do this. But we're going to start with some drone work, which is something that we just piloted a couple years ago to make sure this works. And here's a picture of the drone in the top right. And then we flew it over this forest on the left. And every magenta dot you can see there is a palm species that we identified on the ground. So we were wandering around the forest and we were using a GPS and figuring out where those palms were. And then we flew the drones over and we took lots of images. And then using the GPS and the drone, the species that we found. And what we were doing with these images is figuring out, which ones were palms and circling them. You can see here. And then coloring them by species, of course. And then using machine learning and some artificial intelligence to see if the computer could identify the trees from the air. And you can see one of our first tests. You can see on the left some palms poking out of that forest canopy on the right. This is what the computer thinks it's seeing. And the computer was over 95% accurate in terms of comparing our work to what the artificial intelligence was doing. And this is really amazingly going to be really neat because we can fly this drone over thousands and thousands of square kilometers of Amazonian forest and automatically identify these canopy palms and know exactly the scales at which these common species are common and the rare species are rare. And then studying through time, when you look at soil cores and soil profiles, this is a picture of a research project in Brazil. You can see the top part of that soil core here is kind of dark, and that is because of sustained burning through the years. And so you can look at a soil core, and here's a soil corer, and you can use a microscope and you can find pieces of charcoal. You can use radiocarbon dating to know exactly how old it is. And then what I'm looking at here on the right are these things called phytoliths, and phytoliths are these silica bodies that you can find in the leaves of palms and some other species. And the thing that's really crazy about them is they accumulate over thousands of years in the soil column, and you can measure them and date how common different species were over millennia. And you might be asking, what does all of this have to do with sustainability? Well, I think it has a lot to do with sustainability. I'm going to tell you why. And it's that we know that people can take care of forests and that forests take care of people. And they have been doing so for thousands of years. These palms, for example, provide key nutrition and food for people, as well as a lot of materials. And so it's not that people are using forests in a negative way necessarily. It's how people use forests. And when you read about the Amazon, you hear about deforestation and industrial agriculture, the fires that people set to make larger areas for cattle ranching or soybean production. Gold mining, and this has been going on for ever since the Western world basically showed up in the Amazon. This is a picture of somebody doing rubber tapping. Rubber was the first kind of black gold of the Amazon. It was at one point the most expensive substance on Earth. But the local people that live in the Amazon have never benefited from really any of these economic ventures, whether it's oil, gas, rubber, ecotourism. Very little local benefit. And when I think about sustainability and I think about some of the challenges we have about climate change and biodiversity conservation and social justice, I think it's important to note that these three goals don't always completely align. Sometimes people get really excited about putting up, say, solar panels in the desert because it's going to, save us a lot of energy, but that is, destroying critical habitat for desert species. So those goals don't always align, right? And the same thing with social justice. And what we want to do is work on this sweet spot where we can simultaneously prevent climate change, work on social justice, and also biodiversity conservation. And this project, we're developed some climbing gear for the people. That really mimics what they've already been using for thousands of years, but it makes it safe. They can't fall out of the tree when they're using our gear. And palm fruits are actually one of the really successful examples of how people can sustainably collect fruit in the Amazon and sell it, both for local markets and international markets. One example is acai. Sambazan is a U.S. company that makes over $500 million a year doing sustainable harvest of fruit in the Amazon. And none of this work can be done, though, without participation with so many different kinds of people. Scientists from Amazonian countries, students, and people who live in the forest. And that's frankly, my favorite part about my job is going and getting to know some of these people and doing research that I think can hopefully make a positive impact on the world. So I want to encourage you to contact me directly. There's my email right there if you have any questions, and I'll be happy to take any questions later on. Thank you.
Thank you very much, Paul. So we do have time for a few questions. So actually, well, maybe it's a complicated question, is your work clearly has importance for long-term sustainability. And so what are the mechanisms you're using to make sure that your findings sort of are made useful to NGOs or other scientists or other sort of organizations? Hard question, perhaps.
Yeah, but that's okay. I mean, I think the more we elucidate the extent that people have been managing forests, and we understand whether this was an impact that was only, relatively recent or on a smaller scale, or versus sustained over many years and over a huge area, it's going to allow us to think about how people have been taking care of forests and thinking about solutions for the future.
Yeah, okay. I'm also intrigued just how many species of palm are there in the Amazon, and how many of them are actually of nutritional value and therefore perhaps economic value to the local peoples?
Well, of the top 20 most common trees in the Amazon, about almost half of them are palms. Mm. And most of those extremely common ones produce nutritious fruit. There's one that I particularly love. It's called Onocarpus patawa. It has complete protein. So there's a tribe in Ecuador. They send their youngsters out in the forest for a whole month, and the only thing they're allowed to eat is this palm, because it gives them all the protein they need. But there's other palms that have high, vitamin E, oils, healthy fats. But you asked how many species of palms there are in the Amazon. I think there are about 400 species, if I'm not mistaken.
Okay, wow. So here's a question from Eve and Jerry Lerman. Are discoveries like Taxol likely to come from this research also? You might want to explain what Taxol is, because I don't know what it is.
Is a drug that is used really effective against breast cancer that was discovered in the yew tree in the Pacific Northwest. I will say that palms are likely to be really important for nutrition and not so important for medicines. But there are so many other species in the rainforest that are, like, we use curare, for example, is a rainforest product that we use in anesthesia, and there's so many other kinds of drugs that are being developed from rainforest plants. It's one reason why people get really excited about rainforest conservation.
Judy Green asks, what percentage of the rainforest has been lost?
Well, there's intact forest, and there's logged forest, and then there's secondary forest. So some of the forest regenerates. But the one thing Amazon has a really, so the answer is about 70% of the forest is still left intact, 70 to 75%. But there's a larger percentage that is regenerating. And the reason is that there's such a high total there is because there are so few roads that go into the Amazon basin. And it's hard to bring the tractors and the equipment to a lot of these areas to do large-scale forest clearing at present. But the Brazilian government and a lot of the other countries have invested a lot of money into building new roads. So that is one really something that we really need to be concerned about as international people concerned about conservation.
Okay. So I think what we'll do now is move on to our next speaker, but there will be time at the end for questions of any speaker. So if you have questions that occur to you as you're listening, type them in the chat and we'll see if we can get to them then. So thank you, Paul. And it's now my pleasure to introduce Alesandra Lanzara. She's the Charles Kittle Professor of Physics and the founder and director of the Center for Sustainable Materials and Innovation. She studies new materials such as two-dimensional materials and superconductors and explores ways to engineer novel quantum phenomena. So we're going from trees into new materials. Alessandra will take us to the high-tech world that literally is at the interface of biological materials and material science. Alessandra, the screen is yours. Can't hear yet. You're on mute still. Excellent.
All right. So thank you, Charles, and welcome everyone. And it's really a pleasure to virtually meet you all. I hope in the future we can meet in person. And I'm excited to share with you today how the incredible opportunity in material science can help us solve one of the greatest challenges of our century. And I hope that this presentation will inspire you, your imagination about the next frontier of material design. So the incredible standard of living the new technology have enabled today comes with an heavy price for our planet, with the depletion of natural resources, landfill, and poisoning water and field. Electronic waste is just an example, and it's crazy to think that just last year we threw away 60 million tons, which is the equivalent of 1,000 laptops per second. And one of the big problems really is that when today we design a new material, we define good, the ones that have very high performance. Then we avoid the bad, the toxic, and the radioactive one. But sustainability metrics like recyclability and ease of disposability are not considered at all. So we can turn to nature for inspiration. And through eons of evolution, nature has developed a very sophisticated building block like the DNA, contains all the information needed to build a more complex structure. So for example, if you take many of these strands of DNA and you put them together, they will automatically self-assemble in all of this structure, from flat, smiley face to three-dimensional box that can open and close. This process is called DNA origami. But DNA can also do more complicated structure like the protein. And protein, by simply changing their shape, can change their function. And for example, one of the functions is to assist ion transport in and out of a membrane or a cell. And this is what governs the signal transfer between the neurons in our brain. So by binding into very specific site, the protein can make these ions go through. So the dream of material scientists today is whether we can reach the same level of control that nature has achieved. So the way we design material today is atom by atom. And we will hear more about this exciting research direction from Ramesh. The way the atoms arrange themselves control the final property of material. So for example, if you take this material that we are using for magnetic RAM in computers, its property, once you grow the material, fixed. And the process to engineer it is often very energy expensive. The recent Nobel Prize discovery could actually provide the solution, because now we can isolate individual layers starting from a three-dimensional material. And this actually was literally done by using a Scotch tape. The way, an easy way to think about this process is like if you are pulling out a card out of a deck of cards. And this card by itself is going to have very well-defined property. So for example, it can be a perfect metal, a semiconductor, or an insulator. Today, this method is applied to a variety of materials, and we consider this the building block. And so what we can do, just like with DNA, we can start to play Lego. So we can start, for example, to building structure one layer at a time, or by twisting them. And this process completely changes the property. Tunic, for example, you start from two layers that are insulating and they become superconductor just by simply twisting the layers. Or you can turn, for example, two insulators, putting them together into a perfect conductors. The technological applications are obviously endless. And just to give you an example, we can think about foldable, printable electronics, as well as think tomorrow to have a computer that you can fold and put in your pocket. So here in Berkeley, we are working to realize this vision for creating a new material that is sustainable. And our approach is really to combine the building blocks of both systems. So on one hand, the building blocks, this two-dimensional building block, because they bring superior performance, which is what you need for any device today. And on the other hand, we have the building block coming from biology that will provide the sustainability via self-assembly and energy efficient manufacturing. So this is an example of how the dream material will look like. The sandwich structure represents now a full working device. So for example, think about a transistor. This is like your next transistor. So the two layers material, we start with the substrate ions, and by the exfoliation process, we put these two layers, one on top of the other. And what they do, they will provide us the high performance you need today in any, for example, electronic device. Now the DNA origami and the protein come and they self-assemble, and they can make manufacturing now very easy, very energy and time efficient. And in addition, the site-specific where they go allow us to reach miniaturization beyond what we can do today in the semiconducting industry. Sustainability obviously comes from the fact that this structure bond with the layers with very weak bond, so you can break them when you want. And finally, when you change the configuration of the protein or the origami in between, ions start to flow. And this is how you define and you control the properties. So all you do is pretty much you obtain multiple functionality from a single device. For example, you can convert by changing the protein configuration of your device from being a transistor to be a superconducting sensor. And when you are done, the structure itself can be disassembled and you go back to the individual component and you can reuse there as you want. So we are really already starting to realize this vision. And in my lab here in Berkeley, we are developing a new technique to grow this very large wafer, because indeed this is what you need for technology. And we are then optimizing the way we extract this single layer. We then build the structure made out of different layers, or also inserting ions in between. And then we study properties such as the gap, which is the basic component of any transistor, and how it changes when you, for example, change layers or what you put in between. And then we study properties like mobility, which is nothing else than a measure of how current flow. At the same time, we are exploring ways to control protein folding. So protein exists in many different configurations, and each different configuration has a completely different functionality, which enable the many things that we all know protein can do, from, for example, sending an electrical signal or enabling vision. So what we want to do, we want to use the light to control in which formation my protein ends up. And this is ultimately what I would like to do to make this programmable device like the one I showed you before. And here, let me share you one exciting, very recent result from the group. So we prepared the protein in this solution, then we shine light, and we can see that by shining light, the protein exchanges its conformation. And we can test this by looking at the fluorescence emitted from the protein. So in conclusion, I hope that with this presentation, I've inspired you to the exciting possibility that we had ahead of us, and how transcending the boundary between traditional discipline is really the potential to reverse the unsustainable trend we have taken today. And this will help us leave a beautiful planet to our kids and the generation to come. And I thank you for your attention.
Thank you very much, Alessandra. That was fantastic. There's some notes in the chat of the importance of Charles Kittle in terms of textbooks, and sadly passed away last year. But Alessandra has a chair named after a legend.
Yes, Charles Kittle was a professor in our department, and I think pretty much all the material scientists and condensed matter physics like myself, we grew up studying from the book. So actually, I was hoping when I was coming from Italy to, in a way, you know, do something following his legacy. And so he's definitely a very important pillar of our department.
So you said that this process of combining the sheets with the biological materials enables you to miniaturize. How much smaller do you think you can get, and why is that important?
So we can go down to really few sub-nanometers, which is well beyond what you could do today. Well, if you think about a device, for example, in your telephone, in your computer, we are always, because of the famous Moore law, we are always trying to make devices smaller and smaller. And there is a limit on how small we can go. And one actually of the limit is that when today we use all this technique, lithography, or this manufacturing technique to make our device, there is a limit on how small we can go. So if we let nature do it, the protein or this DNA origami, they know exactly in which specific site you go, and they do it down to the nanometer. So you could really build like channel and attach this channel for conduction in the specific point you want and you need. So now you can think to make this device smaller and smaller and smaller.
So how much smaller is that than the current size for the same functionality?
I think for the same functionality, well, I mean, the system obviously will give a completely different functionality, but for if we think in the same way and how small I could go, I think we are talking about tens and hundreds of nanometers today. So it's definitely at least 1 to 2 order of magnitude better.
Okay. So we have a question from Rona Gifford, who asks, how stable are the biological materials? Aren't they readily degraded?
Sorry, can you repeat? I was trying to exit from the screen sharing.
So the question is, how stable are these biological materials? Aren't they readily degraded? How does that work?
So it depends the type of biological material you use. So for example, DNA origami are pretty stable. And there is a very broad field of research actually that is already trying to make all this different structure using DNA origami. So that's definitely the first direction to go. There are, as for protein, there are some synthetic version of protein that we are already using today, like for example, the peptide. And this will be the first natural alternative for making this structure.
So a hard question is, how far are we from real world applications with these new materials? They're clearly extremely exciting, but yeah.
So I think the good news is that we are already testing and demonstrating the feasibility of the concept. But obviously from demonstrating a concept to go down to application is going to take a little bit longer. And I believe that 5 to 8 years, we should be able to see real application of this system. I believe that what is really holding us back today is the current funding environment, which is structured in a very silos way. So it's easy to find funding for inorganic or this two-dimensional material as well as biology. But there is really nothing that is interdisciplinary between the two areas. And this is, I mean, it's coming more and more clear that this is really the future of material science. That's the direction where we want to go. And so this is what today we hope a funding agency will soon realize, will catch up with the, where the research is today.
And can you give us a little taste of what the first rollout application might be? Will it be in our cell phones or a sensor in our house?
I think, I mean, the first, if we can, the first successful thing, which is what we're shooting for, to prove it that you can actually use this structure to work as a transistor, and then to make it also work as a sensor, this will open up a really application in all, obviously, electronic, because as you all know, the transistor is really the building block of electronic.
Okay. Well, thank you very much. Again, I remind everybody that we will have time at the end for questions. So if questions occur to you, please type them in the chat. And so now, let me see. It's my pleasure to introduce Ramesh. He is the Purnendu Chatterjee Chair in Energy Technologies and is a professor of physics and materials science, also a faculty scientist at the Lawrence Berkeley National Laboratory, just up the hill from the campus. He explores the properties of new materials, in particular correlated oxide thin films and heterostructures. He served as the founding director of the Department of Energy's Sunshot Initiative, that's at the federal level, and is a foreign member of the Royal Society in the UK, as well as a Berkeley alum. Ramesh will take us down to innovation literally at the atomic scale and its relevance to solving energy problems. Ramesh, the screen is yours. Still muted?
I'm still muted.
Yeah, very good.
Okay, thank you, Charles. Thank you all for joining us today. Thank you, Francis and Mike, for giving me this chance to give this short presentation. As Charles mentioned, I work at crossroads of science, for sure, solid state physics or condensed matter physics, as well as technology. I have a joint appointment in the engineering college as well here. About a decade ago, I had the chance to work in the Obama administration. I ran something called the Sunshot Initiative. It was modeled after the Moonshot Initiative, which was the Apollo program. How do you solve mission impossible big problems? And that ethos really, it stuck with me a lot. So I look at problems, and I'll show you a video in a second, problems at the macro scale with energy as a convolution function, but use science and technology as a pathway to solve these problems. And as a default, I've gotten a lot more into policy. I actually teach a class which some of you know, Rich Mueller, Professor Mueller taught this class called Physics for Future Presidents, and I teach it now. And I really enjoy teaching this class because it's at crossroads between all of these four topics. And that's what this kind of enmeshed gear is telling you, that these things are going in and out of each other. They're very difficult to separate out. So I want to start with a summary of my talk. And this is a video that one of my twin daughters produced for me. She's a design major, but it's taking you through from global economics, how you look at a big problem, come down to the technology space, in this case, AI, machine learning. And then from there to go to the level of electronics, energy efficient electronics. From then go to new materials discovery, new physical phenomena that we in materials physics like to explore, go all the way down to the atomic scale. What you're seeing here in this last video is really the hydrogen atom, electrons going around, and how its motion in the orbit around the nucleus changes its behavior. It's so-called spin orbit coupling. So that's going to be the theme for the next 6 minutes or so. So with that, let's ask the question, can we create energy efficient computers which are 100 times more energy efficient than today? The first thing you say is, okay, why do I want to do that? One of the big reasons, if you step away and look at the global perspective, there are three things that are happening, phenomena. One is the notion of artificial intelligence. Paul talked about it. You can use these drones and use the computer to find out what kind of plant it is. And this is the whole idea of machine learning. In parallel, there is another notion that's happening, which is called the Internet of Things. The entire roadway system, hospital systems, all of these macro scale systems are connected with microelectronics. So those are driving exponential growth of these technologies. And that's the red arrow that you see here. The first red arrow is telling you that the deployment of these kinds of technologies is growing exponentially. Indeed, you can have a driverless vehicle today. It doesn't work very well because it cannot compute fast enough. It needs a lot more energy to compute. That then translates to this plot that you see in the background, which is plotting the percentage of primary energy as a function of year. And it says that if I do nothing to today's technology, but I keep deploying these at an exponential rate, then it's likely that by 2030, not very far away, a decade away, we could be consuming 25% of primary energy. When you say primary energy, that means, God forbid, another coal-fired plant or a natural gas plant or a new source of energy is needed. Just to give you a point of reference, today in the United States, we use about 25% of our energy for transportation, about 38% of our energy in heating and cooling buildings. So if your computing operations worldwide is about 25% of primary energy, you need to sit back and say, that's a large amount of energy. How do I make it more efficient? Therein lies the challenge. So if you want to change something by 10%, you can go to the engineers and say, make it a little bit more efficient. If you want to change it by 2 to 3 orders of magnitude, you actually have to go back and do fundamental science with this, because you have to discover new pathways. And that's what has led in the past. And this chart is from our friends up in Portland, Intel, which talks about the heat output. And if you touch your computer, you will see that it's getting pretty warm. That's because all these chips are producing a lot of heat. And if you look at 2 previous generations, the so-called bipolar, invented in Bell Labs, which is where Francis and myself, we worked a long time ago, you could see that they take off quite a bit in the heat output. That's telling you that the technology is working, but it's putting out too much energy, wasting too much heat. That transition to a newer technology called the CMOS, complementary metal oxide semiconductor, for those of you who are following these technical jargon, but you could see that that's also reaching a very large peak in energy consumption. And therefore, the entire community, the science and the technology and the business community, is now expecting a transition to a totally new way of looking at it, which has 100x more efficiency built into it. And therefore, we think that this is going to be driven by physics, the fundamental physics, and the materials discovery part of it. And the question is, how does one go about doing it? Enter materials that Francis, myself, Alessandra, many of my colleagues in the department, we look at. Now, I'm showing you a very simple analogy just to make the point. The way you build today's transistors, the computers that you use, is by using electrons. And these are, I call them simple electrons. They're not simple, but they're already complicated by themselves, but they're simple because they're running around everywhere. They're like the fish here. They're going all over the place. What we want to transition to is to a scenario where these electrons are like the fish on the right side. These are schools of fish where they're all moving in the same direction. There are microscopic interactions between this fish. Paul and Charles will tell us what those interactions are, but there are interactions. These are called correlations. Birds flying in a formation is another example. The evolution of a mob is another example. These, in our language, in our quantum mechanical language, are called correlated electrons. They sense each other. There are other physical phenomena as well that one can use. So then you say, okay, if I can use these phenomena, how do I go to make these materials? How do I design them? And therein comes our materials chemistry. These are the materials that people like Francis, myself, Alessandra look at. It looks like it's a very complex jungle. We will untangle it. These are materials which have composition of A, B, and oxygen. A is a big ion, it's a space filler. B is the most important player. It's a material like iron, a very, very pervasive element. But if you look at this thing here is the building block. It is the apartment complex that you have, and you can twist it, turn it, you can stretch it, you can rotate it, and all of the properties start to change. The electronic properties change. So these octahedra, which by themselves are built with the electrons in the atoms, these are the orbitals of the electrons, you can start to manipulate them. They can turn, they can twist, they can interact with each other or completely stop interacting. So you can that can lead to a whole host of physical phenomena. Okay, then you say, okay, I got that. Our chemistry colleagues teach us that. How do you make these materials? That's where people like myself come in. I make materials one atom at a time. What we do is to hit a ceramic piece with a laser. And that's the laser coming in, and it's evaporating material, and you capture it one atom at a time. And by the time you're done, you will see the next slide that you have now made a perfect material, absolutely perfect material. And so you say, how do I know this is perfect? We can go to the most powerful electron microscopes. We happen to be very close to a national lab here at Lawrence Berkeley lab. And these are what you see as the dots here are atoms in the material, in that material that we grew. And I can go and enlarge it a little bit. You can see that these are the lead atoms, the big atoms, and these are the titanium atoms, which are the small atoms, and so on and so forth. So you can now look at the structure of these materials. Indeed, you can look at the electronic structure of these materials with atomic scale precision. You can design them in a computer, make them with these precision techniques, and then look at them. Then you say, okay, you said all of that, that's fine. Is it really true that you can go to very low energies? This is data from our work, a whole bunch of folks here working on it. Indeed, in just 3 years, we have gone from 5-volt operation to 0.5 volt. This is manipulating a magnet, a ferromagnet, with an electric potential of just 0.5 volt. Plus or minus, you could see with plus 0.5 volt, it is north pole pointing up. With minus 0.5 volt, it's north pole pointing down. These are images of the magnet showing it's bright, white, or dark. And therefore, these are the zeros and ones that you can start to program in. Our goal is to go below 100 millivolts or 0.1 volt. And at that point, the energy consumption is going to be of the order of an attojoule. Attojoule is a 10 power minus 18 joules, much, much smaller than what we are consuming today. Okay, so that's where we are. Now, the fun part of all of this is the following. The story I told you was mission-driven research, where we said, hey, we want to solve a big problem. We go down to the basics. One of the fun parts of doing fundamental science is all the unexpected discoveries. Now, this animal that you see here, it's called a skyrmion. It's a very unique object in solid state physics. Think of each of these arrows as twisting and turning dipoles. In some sense, it's an atomic scale tornado. In some sense. I'm going to show you a video of this. This is a very unique object, and it's a big fascination. I'm going to take you right through all of these atoms, these dipoles that are swirling around in space. But with the precision materials design, synthesis, and probes, we can start to create these new objects. This was completely unexpected. Why is it unexpected? The reason is that you took two materials which have very different properties, of course. You put them together, they have handed behavior. You see these arrows here, the arrows are going from left to right. They could also go from right to left. So these are chiral objects. So imagine that you could take D-glucose and apply a field to it, an electric field, and make it go to L-glucose. The glucose that we do not assimilate. We now have the power to do those kinds of things. So with that, I thank you very much for your time. You have my email contact at the bottom. Very happy to answer questions. Charles, I hand it back to you.
Thank you, Ramesh. We have a couple of minutes for questions for Ramesh, and then we'll have a few minutes for questions for anybody if you'd like. So Ramesh, in one of our discussions, we had a conversation about the energy usage, how that we partition, say, in self-driving cars. Can you give those numbers?
Yeah, that's a great question. So a few years ago, we did this calculation. It turns out Google, for example, is making all of these things. They're trying to work on it. The calculation was the following. If you take a Tesla, many of you guys drive a Tesla, it has about an 18 kilowatt battery. And if you wanted to convert your Tesla to driverless vehicle, some calculations show that you can consume up to 70% of the battery power to just drive your computers. So your range went from 300 miles to something like 40 miles or 50 miles. And so that gives you kind of a feel for how much computing is required. And of course, some other people will tell you, okay, it's not 70%, it's 30%, but it's a very large number. And therefore, it is still not practical enough to take a car and make it completely driverless.
We have a question from Ken Hart. Is there a false belief, that's sort of a similar question, that electric vehicles are truly as environmentally friendly as advertised? Do you end up requiring more primary energy plants merely as a substitution?
Ken, that's an awesome question. The question that you're asking is it just enough that I put a battery in my car and therefore I have been sprinkled with the holy water? The answer is no, because in order to make the battery, in order to keep it charged every day, you've got to get electricity from the grid. And the question is, where is that electricity coming from? But what is happening also, Ken, the positive part of it is that because of things like Sunshot, when we did Sunshot, 99% of the people said, you guys are crazy. You guys are smoking something in California. We said, yeah, we know that, but this is not impossible. And today the same people say, oh yeah, it's no problem. Solar is going to work very well pervasively. And once that happens, the net energy consumption to run an electrified vehicle is indeed going to come down. but you have to work in the cost of, or the energy cost of making the batteries. And that's not a trivial cost either. So it's the full integrated cost analysis that needs to be done.
Yeah, okay. So I think what we'll do now is open the floor to questions to anybody. I've got a question for Paul, which is, there's a sense that it come out of ice ages and backwards and forwards, that the Amazon forest may be contracting or shrinking and then re-expanding again. And so one of the questions I have sort of related to that is, when you core down looking at the history of management of the forest, how deep in time do you actually go? Is it 100 years, 1,000 years, 10,000 years?
Yeah, it's more in the range of a few thousand years. Yeah, and but there are some archaeological sites, I think over 10,000 years, showing that people are using palms. So, yeah, I think that there's going to be, and there are other ways that you can get information from deep time through some of the coring that's done, and some of there's a few older lakes that have been around that you can get pollen cores from. And then the oil industry has all of these coring in Colombia. And all that data, of course, is proprietary, but there's a scientist who has made a deal with the Colombian government, and they're sharing all their pollen data with him. So we're getting a lot of interesting data from past rainforests in Colombia.
Okay. So actually that comment leads me to another thought, is that we tend to think of science in terms of great people, individuals, but of course it's always built on the framework of the institution and all the support and the colleagues. And so sort of related to that question, Alessandra, it's a hard question perhaps, but how do you go about finding the proteins that are going to be of most interest or of most use? You start off as a material scientist, now you're sort of becoming a molecular biologist. How does that work for you?
I think this is one of the great advantages being an institution like Berkeley. There are colleagues throughout all the campus who are extremely smart, motivated, enthusiastic, and are doing incredible things, really at the frontier of science. So how do you go about it? You meet, you talk, you exchange idea, and that's how I actually hold this sustainable material project started. I reached out to a colleague of mine, Carlos Bustamante, who many of you might know is really a pillar in biophysics. And we were discussing about some new tools I had developed in my lab for controlling quantum materials. So I'm coming from material science, working on quantum material, this complex structure Ramesh just talked about. And we had developed this new tool. So I reached out to him and I said, I think we could actually apply this to look at protein. And then one discussion led to the next. He brought in another colleague. I brought in a colleague of mine. And then we brought in Ali Bisatos. I mean, the things start to grow. And that's Frances joined the discussion. And that's how this whole idea of how can we make this sustainable material came through.
Yeah.
And
hey, can I add a point to that? I
yes.
think, the other really fantastic thing about Berkeley is the student base. This is a virtual tornado that's continuously spinning.
I was getting there, Ramesh.
Yeah, please talk about them. Yeah. Go ahead, Alessandra.
No, you go ahead.
Yeah, so I was going to say that both at the undergraduate and the graduate level, we have some amazingly committed students. Their commitment to just a broader perspective, not just physics or electrons and photons, but the society at large is just very fascinating.
Yeah, just as part of the community. And of course, often they have fresh ideas and handle sophisticated tools more easily than those of us that get older. So
I always tell students when they come and visit Berkeley and they don't know where to go, I always tell them my experience at Berkeley over the year that is reinforced is like ideas are floating everywhere. You just have to, put the head outside your door, grab an idea and go. It's such a vibrant and incredible place. And as Ramesh said, at the end of the day, the students are really the one that make things happen and make collaboration work.
Right.
And so, Paul, are you taking students into the rainforest?
Yeah, and so this project is in collaboration with with one of my PhD students, Giovanna Figueroa, and then we have a whole group of students that we'll be working with in Peru, and in Brazil and in Colombia and in Ecuador. So yeah, it's a mixture, and everyone learns from each other, and it's really a lot of fun.
Yeah, very good. Well, I think, sadly, our time is coming to a close. Thank you very much, Ramesh, Alessandra, and Paul, for taking the time this evening, and for you all. And so, to close out, it's my honor to pass over to Mike Bochen, the Dean of the Division of the Biological Sciences. Dean Bochen is Professor of Biochemistry, Biophysics, and Structural Biology at Berkeley. Having received his PhD from Berkeley in 1972, Mike was recruited back in 1980 to become an associate professor in molecular biology, so recruited at a senior level with tenure. His work has included deep contributions to virology and to the unraveling of the mechanisms of DNA replication, which we've been in communication about recently. He is a member of the National Academy of Sciences and the American Academy of Arts and Sciences, and a fellow of the American Society for Microbiology. He chaired the biochemistry section of the National Academy of Sciences and is still a member of the editorial board today, and currently chairs the medical advisory board at the Howard Hughes Medical Institute. Mike, the floor is yours.
Wow, I've heard the word amazing several times from Ramesh, and this is just so inspiring. And thank you, Charles, wonderful moderator. And thank you, Paul, Ramesh, and Alessandra for sharing with us your work and the glimpses that you all gave us into how basic science can advance our efforts to address this very important issue of sustainability and deal with climate change in a way that is just, as Paul emphasized. As a dean and a scientist, I'm inspired by the excellent science and the results it does generate to address the existential threat posed to life on our planet by climate change in what has been named the Anthropocene epic. Excuse me for screwing up both those words, but this is a man-made epic in the geological time of the Earth in our planet's evolution. I want to say a special thanks to you and our alumni and friends for being here tonight and sharing this event with us. Tonight's event is intended to shine a light on climate change, but our series of science talks more broadly help us to convey the importance of basic science. And I think you've heard that emphasized throughout the talks. I feel really strongly that while it's essential to apply our science to solve problems, it goes hand in hand, this discovery, with the foundational work that leads to those solutions. Basic science has always been Berkeley's greatest strength and must continue to be so and will continue to be so. And I'm so invigorated by what I heard tonight. Your support and your advocacy for Cal means everything to us and to the faculty, those like Charles, Paul, Ramesh, and Alessandra. And they're incredible students. While extremely gratified for your continued interest in Berkeley, alma mater to many of you and the fantastic work done here, I'm extremely gratified by the size of this audience and the fact that you've stayed with us for the full hour. If there's anything you want to learn about, or if you'd like to support our work for which there is a deep need, please be in touch with us. We absolutely want you to be part of advancing basic science and discovery at Berkeley. And with that, good night and fiat lux.